Spectroscopy and fluorescence. Light is made up of massless particles known as photons that behave as waves. This lab focuses on their properties as waves and the visible light spectrum. The visible light spectrum is measured in nanometers and runs from a minimum of 380 nanometers violet to 750 nanometers infrared. For this lab, we use these principles to determine both the absorbance and the fluorescence spectra of the sample fluorescein. Fluorescence measures the wavelength emitted by a specific compound when a given specific wavelength is shown to the sample. Absorbance measures how much of a wavelength is absorbed by the sample. If more wavelengths are absorbed, there will be a higher concentration of dye in the sample. Fluorescence data needs to be collected differently to avoid measuring the intensity of the source light. Absorbance can be determined from measuring intensity of the light through a sample and a standard solution using the equation A equals log I initial over I1, where I initial is the intensity measurement through a blank standard and I1 is the intensity measurement through the sample.
For our experimental design to measure absorbance, we use a fiber optic cable and Pasco spectrometer and the corresponding software to set out to determine both the absorbance and fluorescence spectra of fluorescein. Prior to sample measurements, a standard was taken using pure water. To measure the absorbance of fluorescein, a flashlight with a concentrated beam was placed at 16.5 centimeters away from a cuvette containing fluorescein, and the fiber optic was positioned against the cuvette on the opposite side of the light source. The Pasco computer software was used to interpret the data input, and the absorbance values were converted into data points in an Excel spreadsheet. And for the fluorescence determination, the light source had to be placed at a 90-degree angle to the light detecting cable so as to avoid light from the source being detected by the cable. The fiber optic cable was placed at the point on the cuvette at which there was the most luminescence emitted from the material. And for this test, the standard using water was measured prior to measuring the sample. And these were our results. The orange line represents the absorbance spectrum of fluorescein, and the blue line represents the fluorescence spectrum of fluorescein. And these measurements are scaled down so that they could be viewed side by side. So spectroscopists can determine the identity of an unknown sample by examining the sample's absorbance and emission spectra. As the sample is exposed to a wide range of wavelengths, the electrons of the molecule move into an excited state, and as they return to their low energy state, they emit a specific spectrum of light. The specificity of the emission spectrum of the unknown sample allows it to be identified when compared to other compounds with known emission spectra. Beer's law is an equation used to determine the concentration of a solution after measuring the absorbance, where A is a unitless measure for absorbance, epsilon is a compound-specific molar absorptivity, L is the path length, and C is the concentration of the solution.
So most fluorescing molecules absorb a broad spectrum of wavelengths and emit a smaller spectrum of wavelengths lower in energy. This causes a shift in color. As seen in the image below, a higher wavelength of light comes from our source. From there, particles with the same sample become excited and absorb some of the light. From there, the particle will oscillate in an excited state until it gives off energy, returning it back down to its ground state. This emission of light energy produces a different wavelength of light than we started with, and thus produces a different color. Energy is not conserved. Energy can be lost to the surrounding atmosphere in the form of heat.